Hello, I'm James Curran, and it's really good to be speaking with you today, although it's a pity I can't be there in person. This presentation takes its key elements from the paper referenced here, published earlier this year, as well as two previous papers from almost 10 years ago. But I'll take the opportunity to add in discussion of some of the underlying assumptions and to add in some additional examples of the real-world consequences. This expert audience will very well know that human emissions of carbon dioxide, or CO2, are small relative to the natural fluxes into and out of the terrestrial biosphere and the oceans. This diagram shows that human emissions to atmosphere of 9 units, or 9 gigatons of carbon per year to be precise, is partly offset by 3 units per year stored or sequestered by the land and a further 2 units stored by the oceans. But the thing particularly to note is that a proportionately small change in these large natural fluxes can make quite a big proportional change in the small residual, for example, the 3 units sequestered by the terrestrial biosphere. Reduce photosynthesis by just 1% and you almost half the scale of terrestrial sequestration, if all else stays the same. You will also all know the famous Keeling curve, which for this study is based on weekly averages from 1957 up to 2024, from the gold standard Mauna Loa Observatory in Hawaii at 20 degrees north in mid-Pacific. It's recognized as the best and most representative record of planetary atmospheric CO2. In close-up, the Keeling curve has a sawtooth with a drop in CO2 in the Northern Hemisphere summer when vegetation across its much larger landmass than the Southern Hemisphere puts on leaves and grows, drawing down CO2 from the atmosphere. In the Northern Hemisphere autumn and winter, some, but not quite all, of that CO2 is released back to the atmosphere by, for example, biodegradation or microbial decomposition of leaf litter. I came at this study from an ecosystem perspective because that drop is likely to be a rather direct measure of the activity and therefore the health of the planetary biosphere. The analysis is undertaken by determining the value here of little d, the drop from the interpolated point between adjacent annual CO2 maxima and the CO2 minimum within each year. But is it fair to take that fixed point at 0.33 years? Well, yes, because the phasing of the annual cycle hardly varies, as shown here, for the two periods of 1958 to 1963 and of 2017 to 2019. What small shift in phase there is, if taken into account, would actually strengthen all of the following results that we'll see later. So how does that drop little d here in the Keeling curve actually behave? You can see from this scatter plot that the terrestrial sequestration of the Northern Hemisphere was increasing initially, then plateaued, and seems recently to be declining. The peak occurs in 2009 with 95% confidence of plus or minus 2 years. But let's clean up that rather noisy signal. Everything in nature is rather noisy, after all. Let's put a quadratic regression through those upper interpolated points and another quadratic regression through the annual minima, and then take the difference between those two curves at the 0.33 year position in each year. And you get, of course, a nice smooth curve with a distinct peak in 2008. This trajectory or pathway is very significant, as we'll find out shortly. But you might ask, why are you using quadratic curves even though the statistical fit is very good? Well, for several reasons. Principally because intuitively that's the way nature is likely to respond. The terrestrial biosphere is vast and complex and will only respond slowly and progressively to regional and global pressures. Also, because you should always choose the simplest model rather than something more complex and run the risk of overfitting. And finally, because the Bayesian information criterion, a standard test for choice of statistical model, prefers in every case a quadratic over a cubic regression. But step back a bit. We've not mentioned oceanic sequestration at all, have we? Well, that's because if you look at the left-hand end of this plot, you'll see there is virtually no measurable amplitude of annual cycle of CO2 over the vast and dominating stretches of the southern hemisphere oceans. Oceanic sequestration seems to show no annual cycle and so plays no part in this earlier analysis of the annual cycle in the Keeling curve. If we now take our analysis a bit further, we might logically suppose that the annual increment in global atmospheric CO2, that's capital D in this extract from the Keeling curve, might depend on the size of the previous year's drop in CO2, that's R on this diagram, an independent variable, and also on the magnitude of the previous year's human emissions, expressed here as the independent variable E. In effect, this is a box model of conservation of mass. Apply a multiple regression and you get a highly statistically significant fit expressing D, the annual increment in global atmospheric CO2, in terms of the variables R and E. We saw earlier that oceanic sequestration has no annual cycle, but it is increasing pretty much linearly, no doubt due to increasing parcel pressure across the ocean surface. Human emissions also increase linearly, so the oceanic sequestration effect will be cryptically included in the coefficient of the term E. Let's just check that. Ocean uptake on the left of these two diagrams follows a linear trend similar to annual emissions shown on the right. They match each other almost perfectly also in the rate of increase. Now, things can get interesting because we can use that previous equation for backcasting. If terrestrial sequestration had gone on steadily increasing as it was in the 1960s, then by now global atmospheric CO2 would be at 410 parts per million, that's the red line here, rather than the 431 parts per million as it actually is, that's the blue line. If, however, terrestrial sequestration had decreased since the 1960s at the rate it is now decreasing, then atmospheric CO2 would now be at 480 parts per million. That's the grey line. So the effect is very large. The difference of 410 to 480, that's 70 parts per million, is 60% of the actual real-world increase of atmospheric CO2 from 1958 to 2024. Another way of expressing this big effect is that the slackening, peaking, and now reducing of terrestrial sequestration over the past 60 years is equivalent to having added another China to the human emissions inventory. Or alternatively, in 1959, the increase in sequestration could absorb an additional 300 million tons of CO2 every year, whereas now we need to reduce emissions by 140 million tons of CO2 each year just to stand still. We have potentially lost 17,000 million tons per annum sequestration capacity over that period. And it looks like the effect is accelerating, and by 2050 we may be losing 300 million tons CO2 sequestration capacity each year. But you might say, don't satellites show the planet is greening? Well, maybe so, and admittedly, lots of publications still assume and suggest that terrestrial sequestration is continuing to increase. But many other adverse effects are possibly overwhelming. Heat and drought stress on forests, new pests and diseases reducing primary productivity, nutrient limitation on the fertilization effect of increased CO2, certainly wildfires in boreal forests releasing large amounts of CO2, possible outgassing from enhanced permafrost melt in the northern hemisphere. And there is growing real-world evidence of dramatic reductions due, it's postulated, to climate-induced drought of production in Swedish forests. And also serious concerns being raised of failing sequestration in the Amazonian and the African tropical forests. What should we do? Well, probably the most effective ecological intervention would be to reconnect at scale fragmented natural habitats worldwide. There are long-running experiments in several continents showing substantial enhancement of ecosystem services, including carbon sequestration, resulting from strategic habitat defragmentation. The message is clear. We can only ensure the future by nurturing nature, and of course by ending emissions. Thank you very much for listening.